Hi, I'm Terry Binion, National Sales Manager with Catronix Corporation. Welcome to a demonstration of the principles of solids modeling using constructive solid geometry through the use of CatSolid, Catronix's geometric modeler. What I'd like to do today is demonstrate how an engineer might build a three-dimensional database to construct a typical object such as the one you see here, a 12-inch butterfly valve casting. First, before we build this object, we have to understand a little bit about the principles of CSG, or constructive solid geometry. What we're looking at here are volume primitives. These are the basic building blocks contained in the software which allow the engineer to begin his design. Typical volume primitives can be cylinders, cubes, cones, and spheres. These are the graphic output which can be displayed on the screen and can be unioned together in various ways to build a much more complex object. To begin with, we'll construct the first object using a volume primitive, the element cylinder. We have to define a number of parameters to make the cylinder reality. We have to first define a y-axis. Actually, any coordinate axis will do. We have to define a radius for the cylinder, and we have to define a from and a to point so that the cylinder will know where it begins and ends. Then, if we like, we can define a color, in this case, blue. The next thing we'll do is define another cylinder, and in like manner, we'll define the from, the to point, the radius, and the color, in this case, yellow. The next operation, having defined that cylinder, will be to use the command rotate. And by defining an angular difference and the number of copies that we want to make, we can make multiple copies of this original yellow cylinder. The reason for doing this will become obvious during the next step. This next picture shows the operation intersect, in which we have taken the original blue disc, which was given the English language name subflange, and it was intersected, that is, the yellow holes, which were called just that, holes, subtracted from that blue disc to give us a new element called flange. And you can see the blue and the yellow surfaces very plainly. The next step is to create two flanges. And you don't have to go back and make a new flange. All we have to do in the same plane is mirror the original flange, and we have two flanges now, as you can see here. The next building block is to define the portion of the valve that will become the middle. We assign the English language name middle to a volume primitive, which is a cylinder. Again, radius, from, and to are defined along with the color, which in this case is light blue. The next step is to union together those objects we've just created. That is, the two flanges, the middle portion, and another portion I've called a stem guide, which you see here as two purple cylinders unioned together just the way we union the other objects together. Now it's beginning to look like a valve, but now we have the problem of defining the internal geometry and surfaces of the valve. So we define an object, which in this case is called an internal element, and I'm simply using the English language word internal to describe an object I've constructed from the unioning together of cones and cylinders to conform to the internal geometry of the finished valve. Then, using the command intersect, I will subtract the mass that you see here from the object that you just saw previously to form the finished valve. Here is the final object. Notice that the internal geometry has now been defined, and in like manner, material has been removed from the stem guide, and also material has been removed to form bolt holes in the stem guide. We now have a finished object, again a 12-inch butterfly valve casting, that can now be manipulated in various ways. Having defined this object, what can we now do with the database? Well, one thing we can do is, using a finite element mesh program, enmesh this valve and prepare it for analysis of various types. For example, finite element analysis, in which we could do linear and nonlinear analysis. In this particular case, the engineer might want to study thermal heat lines during solidification of the casting as it cools. Others might want to test stress analysis, and other programs that are commercially available will perform this analysis, and Catronix Corporation can interface this database to any of these commercially available analysis programs. The database can then be used to transfer graphic output via an IGES file, for example, to a drafting system for the production of two-dimensional engineering drawings and production drawings. Another possible use would be to use the graphics output of the solids modeler to send over to numerical control systems for the production of NC tapes for the cutting of machine toolpaths. Now, let's go over to the Hewlett-Packard 9000 32-bit desktop computer and see how this object is constructed in real time. We're now ready to start building this model that we just stepped through a minute ago. The first thing we have to do, starting from the ground up, is build a database. Let me clear the screen. We said a minute ago that this is a menu formatted program. For example, to begin the design, we have to set aside space on the hard disk via menu create. Notice the menu is labeled. It prompts creates a database, creates or renames a model. We have a listing of the legal commands. We can now set aside a database on the hard disk. We go into another menu called Transact, and we see that this database, which we've called Demo, is made current. I've also listed the model and the entity, which in this case is a valve, simply by assigning the English language name. We begin the design by going into Menu Edit. In Menu Edit, we have the ability to pull forth our volume primitives and commence construction of the model. The first thing we begin with is an axis. I define the axis at the center of the screen with these three U, V, and W start coordinates. And I assign the direction with the X, Y, and the Z direct coordinates. In this case, I've given it a Y direct of 1, which is the positive Y direction starting in the center of the screen. I can then begin by adding the first primitive. a cylinder which I've given the English language name sub-flange. You remember when we stepped through the model graphically, we had to assign the axis, we had to assign the radius, and we had to assign the from and the 2 points and give it an optional color. We're now ready to display this object. This object has now been created, and we're displaying it in three-dimensional shaded form. We have control over the view simply by the ability to rotate the coordinate axis through the use of menu View. We're now ready to continue our design. We have called up the cylinder with the color dark blue, and we want to add the bolt holes that you saw in the graphic display a minute ago. So back into menu Edit. We now call up the element cylinder, assign the radius, the from, and the 2 point, and the color yellow, and then we rotate that cylinder to give us the primitive that will become the bolt holes that will be subtracted from this disc here. Notice that we created one cylinder, rotated that cylinder, defined the angle between each cylinder, and defined the number of copies, in this case 12. This is a shaded display of those cylinders that we will subtract from the disc. This will form our flange. To illustrate a little bit more clearly how these holes relate to the disc we're about to subtract them from, it would help to do a simultaneous display. On the left side of the screen, I put the primitive element cylinder, which we've given the English language name of sub-flange. Now, on the right side of the screen, I will add in the cylinders that will become the holes that we will subtract from this disc. This will give you an idea of the relationship of one volume to another, and how we can then subtract these cylinders from this disc. I now go into menu Edit, and I call up the element intersect, and I add in the disc, which is a sub-flange, and I give a minus sign to these cylinders, which we've called the holes. And this is the result. You now see appearing the flange with the material subtracted, color-coded, to form the holes. At this point, it may be illustrative to explain that not only can we display in 3 dimensions, we can take a quick look at our geometry by using 2-dimensional cross-sections. For example, this is a quick plot of this object. Notice that it's displayed in 2 dimensions. It's cross-hatched. It shows the holes in yellow and shows the outline of the flange in blue. This particular operation enables the engineer to quickly inspect the object as it presently exists to see if the operation he's just performed is the right one. The system will not allow him to proceed if he's made a mistake, and he can quickly see using this quick plot method if he's made a mistake. We now want to go back to Menu Edit and create a second flange through the use of the command Mirror. Notice that the mirror command requires that I name the volume that I want mirrored, in this case the flange, that I have to specify the mirroring plane, and that I want the original included. Here's the result. Notice the second flange appearing, and we've got the original flange here. You can see the time this saves by not having to go back and make a second flange from scratch. Simply mirror the work you've already done. We could also translate it and rotate it according to the design we happen to be working on. As we did before, we may want to rotate that perspective and inspect the geometry to make sure we're satisfied with it. Here is a rotated perspective through the center in quick cross-section. I may also want to check my dimensions. So we can automatically dimension this particular object. Relative to the center, I can see that the spacing between my flanges is correct, and that the radius from the center out to the edge of the flange is the way I set it in originally, in this case 9. We're now ready to go to the next step. We want to create the middle portion, so in Menu Edit, I simply call forth another cylinder, give it the English language name of middle, and define it with respect to the y-axis, give it a radius, a from, and a to point, and the color light blue. In cross-section, it looks like this. Notice it's light blue, and it's a section taken through the center of this cylinder. Inspecting the dimensions, it looks like this, and I can just look at it and tell that it's right. I'm now ready to union this object together. In Menu Edit, I called forth the command Union, and I joined together the two flanges, the middle portion, and also the stem guide primitives, which you'll see coming up in purple. Here again, two cylinders union together, which you saw graphically illustrated a few minutes ago. You see the flanges coming into view. Now you begin to see the light blue middle portion. Notice the stem guide primitive is beginning to appear here, and again, it's nothing more than two cylinders union together and then joined to the middle portion. We now have the sub-assembly created from which we can extract the material to form the internal geometry of the valve and come up with our finished model. The first thing I have to do in Menu Edit is define the internal geometry of the valve itself and of the stem guide. Via a union command, I have defined this internal geometry by the joining together of various cylinders and cones of various radii and from and to points to form this internal geometry. What does this mass look like? In cross-section, it looks like this. Here's the object defined here. Cones are in yellow, cylinders are in red. It's just like I had taken building blocks of different shapes and put them together to form this mass. I could even automatically dimension that object to inspect my geometry. Notice that it locates the center and then puts in the dimensions of all the internal element objects relative to that center, so the designer can quickly inspect and see for himself that the internal geometry of this valve will in fact be correct. We can now perform the final subtraction, in which we take the element that we call subvalve, from which no material was subtracted, and subtract this mass out. Let's look at this mass in three-dimensional shaded form just to get a feel for the finished perspective of the internal part. Notice it's coming up in red, and this will mean when we subtract this mass out of the other part that the internal portions will be red, and in just a second you'll see yellow as well, which will correspond to the conically shaped machining marks on the interior surface of the finished valve casting. Some of the cones that were loaded in were so small that in the three-dimensional shaded view we see them as dark black lines and not much yellow, but they will show up in the expanded view of the finished object. Now let's look at this graphically. What I'm doing is simultaneously displaying the internal mass. I will then display the sub-assembly, the sub-valve, and then I will display simultaneously the finished valve, so you can see how we proceeded to subtract this mass to form the finished part. This is the internal portion coming in right now. All right, that's the internal volume. Let's see what the subassembly looks like. And here it is coming in. You can see the flanges appearing. You can see the yellow bolt holes. You'll also see the light blue middle portion. And you'll also see the purple cylinders that will form the stem guide. Now you begin to see the stem guide come in. And we're now about ready to make this subtraction. The software command that I give to perform this subtraction is called an intersect command, in which I give this object here a positive sign, and I give this object here a negative sign. I combine the two together and get the finished object. Now let's look at that graphically, and then we can look at the object in finished form this way. Now we perform the subtraction. And as this picture comes in, we should see that the hole is through the central part of the subassembly, and in like manner, I've subtracted out this portion, a central portion in the stem guide, along with a couple of bolt holes that we did just like we did over here. And sure enough, we're beginning to see the flange. You're beginning to see the interior surfaces of the finished valve casting. Here, the machining marks that we made from cones on this object here are clearly visible, and the colors are very bright yellow. The cylindrical geometry of the interior is red, just like it was color-coded up here. I've rotated the perspective so that you'll be able to see that the material was subtracted to form a hole all the way through and define the interior geometry as well. And then our finished stem guide is coming into view here. Okay, let's blow the image up of the final model. Again, you can see much more clearly the internal portion of the valve coming into view along with the flanges. And you're beginning to see that you'll be able to look right through the valve from this rotated perspective. Begin to see the mid portion in light blue. And now here comes our stem guide. And the bolt holes are obvious. And we subtracted these masses in precisely the same way that these bolt holes were done and the internal portion here was done. We've now completed the model. The three-dimensional database is contained on the hard disk and can be recalled at any time. The display that you see here of the finished valve is now ready for processing via interface to other parts of the user database. For example, we can enmesh this object using the finite element mesh generator and then interface that to a commercially available analysis package. In this particular case, the designer might want to study heat lines and heat patterns as this particular casting cools and solidifies. We may want to take this database and pass two-dimensional views via IGES files to the customer's drafting system. And then he can lay out traditional two-dimensional views to generate production and engineering prints. We can also pass this object information over to the various manufacturing databases, for example, NC tape generation, tool crib, inventory control, and the like, as we've said earlier. What we've done is demonstrated the building of an object using the technique of constructive solid geometry. This is the product called CatSolid, developed by Catronix Corporation as a CAE tool.